Hi everyone, today we're going to get started on chapter 6. In chapter 6 we will be talking about substitution reactions. So we're going to be looking at SN2 reactions and SN1 reactions. Looking here we can see a general scheme. So we have a few terms to talk about. So nucleophile we've talked about before. The nucleophile is what donates an electron pair. So this is going to be donating an electron pair to our substrate or electrophile. Those terms can be used interchangeably. So this is going to be the compound that is attacked by the nucleophile. We have our substitution product. So here's our product right here. And this is going to contain the substrate. However, we are not going to be seeing the leaving group, and instead of the leaving group, we will see where that nucleophile is attached to that carbon center. The leaving group is shown here. The leaving group is the group that is leaving the substrate. So in the lecture that will be following this lecture today, we will talk about different things that make something a good leaving group or a good electrophile or a good nucleophile. So let's talk about the SN2 reaction. So the SN2 reaction, this is very important, it proceeds through a single step, meaning there are no intermediates. SN2 stands for substitution, nucleophilic, bimolecular. So we have our S, N, and then bimolecular is where the 2 is coming from. So the reason that we call this bimolecular, because the transition state of the rate determining step, again, the rate determining step is going to be the only step here because SN2 is only a one-step process. So the rate determining step in the reaction involves collision of 2 molecules. So both the concentration of the nucleophile and the concentration of the substrate will play into the overall rate of the reaction. So the rate overall is going to be a second order reaction. An SN2 reaction is an associative mechanism. What associative mechanism means is that the bonds are going to break and form at the same time. So let's look at a general scheme of an associative mechanism. So if we have this, we would imagine this as our electrophile plus our nucleophile. What's going to happen is at our transition state, we are going to have X and Y, and then we're going to have a bond between Y and Z. So again, this is just our transition state. Our product would be YZ plus X. Again, this is going to be a one-step process. No intermediates will be formed. So if we look at it in this manner where we have a nucleophile, so again, nucleophile is going to donate its electrons to the substrate. So what happens is the nucleophile is going to come in here and attack the substrate. As that bond is forming between the carbon and the nucleophile, this bond here between the carbon and typically a halogen or your leaving group will be breaking. So our transition state here is going to look like this. So here we have a high energy pentacoordinate transition state. So when we look at the energy profile of our transition state, we should have a really large activation energy. And again, that's because carbon does not want to be pentacoordinate. So again, one-step process. So this is just something that's passing through as our transition state. Our product here is going to be this here plus our leaving group. So when we're dealing with SN2 reactions, we have an inversion in the stereochemistry. So we're going to talk about this at the end of this lecture. let's look at this with as methoxy as our nucleophile. We have an attack on this carbon here. So again, this is going to be called a backside attack. So it's attacking the carbon from the backside. So that CO bond is going to be forming as this CI bond is going to be breaking. So we have, again, this transition state. So transition states actually aren't typically shown. You should know what the transition state is, but it's not necessary to draw it out each time. So this is our transition state, again, high energy because that carbon does not want to be pentacoordinate. And our product will have, again, inversion of our stereochemistry. So let's look at the rate equation. So the rate equation for an SN2 reaction. So SN2 reactions are almost always going to be overall a second order reaction. Again, this is because we have, that's where the 2 is coming from in the SN2, right? It's bimolecular. So again, it's going to be first order in respect to the nucleophile and first order in respect to the substrate or the electrophile. So again, overall, it's going to be a second order reaction. And this is where that bimolecular is coming from. The concentration of both the nucleophile and the substrate are going to affect the rate of the reaction. If we were to draw an energy profile of an SN2 reaction, so drawing the energy profile, there's a few things that we have to think about. So first thing, we know that it's going to be a single step. Again, no intermediates are formed in an SN2 reaction. So a SN2 reaction can be either exothermic or endothermic. And as I mentioned, we're going to have a large or high activation energy. And again, the reason for this is because of that pentacoordinate species that is formed as we're transitioning through to the product. So if we have our energy versus our reaction coordinate, we have, again, a very large activation energy. So here's our activation energy. Here as our products, we have nucleophile. So I'm going to write the substrate just as Rx. So we have our nucleophile plus our substrate. When we're at our transition state, again, we're going to have that nucleophile is going to be forming a bond between our R, and then we have this bond here between the R and the leaving group that would be breaking. Here's our delta G. And then our product here would be our nucleophile attached to our R plus our leaving group. So here an exothermic reaction is shown just because the reactants are higher in energy, remember, than the products. So let's talk about the stereochemistry now. So everyone's, I'm sure, very comfortable with stereochemistry, or I hope very comfortable with stereochemistry at this point. So when we're looking at the stereochemistry, SN2 reactions are going to proceed with inversion of the stereochemistry, as I've mentioned. So what does this really mean? So if your starting material or your reactant is R configuration, that means that your product will be S configuration or vice versa. And again, remember, because it's only one step, this is the only way that this reaction can proceed. So let's look at a couple different examples. So if we look at this this reactant here, so again, this would be our electrophile or substrate. Our nucleophile is shown here. So our nucleophile, again, this iodide is going to come in and attack this carbon. The carbon-bromine bond is going to be breaking at the same time. And what's going to happen is we're going to, again, have inversion of our stereochemistry. So the only way for that iodide to attach to that carbon is again going to be a backside attack. And the reason for that is because that IC bond is forming at the same time as that CBr bond is breaking. So now let's look at our configuration. So do we have R configuration or S configuration? So let's start with our reactant. So bromine is going to be number 1. This would be number 2, methyl 3, and our hydrogen's 4. We notice that the lowest priority is pointing behind the page or board, so that is what we want to see. So we have counterclockwise, so we have an S configuration. So since we have a product for SN2, we know that we should have inversion. And again, what inversion is going to mean is that now that we're starting with S configuration, our product should be R configuration. So we have 1, 2, 3, 4. So we have clockwise, which would mean we have R configuration. And again, our lowest priority is pointing behind the page, which is what we want. So again, we see inversion of our stereochemistry. We started with S and we're ending with R. So again, this is a good way to double check yourself. But again, if you think about it, it's a one-step process. So really the only place that that iodide can go or attach to the carbon is going to be on the back side of that carbon. All right, let's look at another example. So we're going to look at chair conformations. I'm sure everyone's very happy to hear that. So chair conformation, if we have something that looks like this, something that looks like this. So if it's easier for you to look at it as a chair conformation, you can do that, or you could also just draw the cyclohexane ring. I'm going to show you both ways, and you can use whatever you're more comfortable with. So if we have, again, this methoxy as our nucleophile, what's going to happen is we're going to come in here and we're going to attack as this carbon bromine bond is breaking. So our transition state here, so we have our bulky tert-butyl group right here. We have our bromine, hydrogen, and then again, we have this penta. So our transition state has this penta coordinate species. And then what our product is going to look like is going to be, again, our tert-butyl is still going to be in the equatorial position. Our hydrogen now is going to be in the axial, and that methoxy will now be in the equatorial. So if we look at this with a cyclohexane ring, so first we have to decide, is it cis or trans? So looking at this tert-butyl, this is pointing up, our bromine's pointing up. So that means that we have cis configuration. So we can draw the cis configuration in the 1,4 position. And what's going to happen is we have, again, that methoxy. It's going to come in here and attack that carbon. This bond is going to be breaking at the same time. And we are going to have inversion of our stereochemistry. So we're going from a wedge to a dash for the methoxy. And then we would have plus our leaving group. So that's going to be it for today's lecture. As I mentioned, the next lecture will be talking about what makes something a good leaving group, what makes something a good nucleophile or an electrophile. So review everything that we've covered, try some practice problems in the textbook, and if you have any questions, don't hesitate to reach out to me. Have a great day, everyone.